Hello everyone, thanks for coming, and today we are going to do a review on week 10's lectures. So in this week we introduce probability and sample space. A sample space is defined as a pair S and P where S is a non-empty set and P is a non-negative function such that its summation over all elements small s in the set capital S is 1. Let S and P be a sample space and event A is a subset of S. The probability of an event A, denoted by PA, is defined as P capital A equals to P small a, summation of P small a, where small a is an element in the set capital A. Let A and B be events in a sample space, which is also called a universe. We can define these event operations. The intersection of A and B is the event that both A and B occur. The union of A and B is the event that either A or B occurs. A minus B is the event that A occurs and B does not occur. The complement of A is S minus A, which is the event that A does not occur. We have some basic properties for the probability on event operations. Let A and B be events in a sample space. PA plus PB equals to the probability of A union B plus the probability of A intersecting with B. Specifically, if the intersection of A and B is the empty set, then the probability of A union of B is PA plus PB. Generally, the P union of A and B is smaller or equal to PA plus PB. By definition, PS is 1, and the probability of the empty set is 0. The probability of the complement set of A is 1 minus PA bar is 1 minus PA. We can also define conditional probability. Let A and B be events in a sample space and suppose PB is not 0. The conditional probability of A given B, which is the probability that A happens given B happens, is defined as the probability of the intersection of A and B happens divided by the probability that B happens. We can define independent events given the conditional probability. Let A and B be events in a sample space. We say that A and B are independent provided that the probability of the intersection of A and B equals to the probability of A times the probability of B. There are also some equivalent conditions. The conditional probability of A given B equals to PA implies the independence of A and B. Similarly, the conditional probability of B happens given A happens equals to the probability that B happens implies the independence of A and B. Finally, we have the famous Bayes formula. The Bayes formula states that the probability of an event A equals to the probability of the event B happens times the probability of A happens given that B happens plus the probability that P bar, the complement of B happens times the probability that A happens given B bar happens. Specifically, because the conditional probability that B happens given A happens equals to PA union intersecting with B divided by PA. If we replace PA with this formula and replace the numerator by PA given B times PB, then we have the famous Bayes formula for linking the posterior probability with the prior probability. Thanks for listening.